Sorry about the delay. We'll get started. We'll have two talks in this session. The first is an invited talk by Professor Sanjeev Kumar. He's from IISc Mohali. And then we'll have a contributor talk after this. So over to Professor Sanjeev. I think it's still getting.
Check. Side. That needs to connect my machine to battery also, please. So I put it in battery also. Okay. Okay. That's it. Thank you everyone, and I'm sorry about the delay. I had to actually upgrade my Zoom. I didn't realize that I had to do that in the last minute. Hopefully it's all working fine now. So thank you, Chandni, for the introduction, and I would like to begin by thanking the organizers to invite me here for this nice workshop. And as you can see from the title, you can make out that I'm not really going to be talking about any specific engineered quantum material here. Instead, the talk is going to be about certain interesting phases of correlated models, and if at all, we'll be actually talking about engineering some effective or intuitive models to understand such complex phases of correlated systems of correlated particles. So I would acknowledge Ramanujan for all the hard work that he has done in this project, and essentially, all the simulations that you would see here, or anything very complicated, that is all carried out by him. And so let's begin. This is the outline of the talk. So I will give a very brief introduction to Kondo impurity and Kondo lattice models, and I think these topics have not probably been discussed in this meeting, although they are very well known topics. So for completeness, I'll give a very short introduction to these topics, and also related concepts like Kondo screening and RKKY interactions and so on. And then I'll touch upon or introduce this topic of partial magnetic order, which is the main theme of this talk. And I'll sort of provide a summary of this from both experimental and theory perspective. And then I'll come to the main idea of this presentation, which is to construct some intuitive semi-classical models to understand this partial magnetic order in Kondo lattice systems. And finally, if time permits, I'll also go one step ahead and say, okay, can you actually think of a fully classical model to understand some of this physics? And then we summarize and look at some possible future directions. Right, so let me begin with this very standard introduction slide for Kondo, Kondo effect and so on. So, when you talk about Kondo effect, the first thing that comes to mind is this resistivity minimum, and that's exactly, the puzzle that it was actually as early as 1930s. This was observed that if you have magnetic impurities in metals, then you will see this resistivity upturn. And it was a puzzle until 1960s, and this was finally explained by Kondo by considering essentially this term in the Hamiltonian, where the impurities, the magnetic impurities, coupled to the conduction electrons, and then you can do sort of a scattering rate calculation to some higher orders in this term as a perturbative term, and the result of that would be that if the sign of this coupling is positive, as it is written here, which means it's an antiferromagnetic coupling, then the resistivity upturn can be explained. And of course, the scattering sort of theory in some sense diverges at low temperatures, where you can then have to, so it essentially fails, the perturbation theory fails at low temperatures, and the picture that emerges is that of the spin being, the impurity spin being fully screened by the conduction electrons. So the success of this idea of Kondo, or the calculation of Kondo, can be measured by looking at such graphs where you can have basically, scaling of resistivity data from different materials and showing this universal behavior, which is the success of this Kondo theory. Right? So, I mean, of course, there are sort of very good references for this. This is a very, very well-known topic, and in fact, I just noticed that there are also ICTS lectures exactly on this topic by Subir Sachdev and Houston, and probably by more people. And there's also a nice lecture note by P.S. Coleman, which students can look at. So now these systems were metals doped with few impurities, few magnetic impurities. Now it turns out we also have materials where the band structure is such that it allows for simultaneous existence of local movements and conduction electrons at every site. And this then naturally extends this idea of Kondo impurity models to Kondo lattice models, where now the term that we wrote down for a single impurity site can be written down for every lattice site. And this is your Kondo lattice model written on a lattice, where this is the kinetic energy of electrons as a hopping term, and this is the Kondo coupling of conduction electrons to localized spins. So in fact, you can look at this particular graph, which shows what happens as you go from the impurity limit to the lattice limit. So this upturn in the impurity limit, where the behavior is not at all metallic, actually, it comes back to the metallic behavior in the lattice limit, except with an addition that you now have to worry about some renormalized masses of the electron. So this is the heavy fermion physics, and in fact, the end limit of this will be a phase which we call Kondo insulator, where in the lattice limit you actually have all the conduction electrons essentially trapped by this Kondo cloud formation. Okay. So far we were worrying about resistivity behavior, but once you talk about the lattice of impurities, lattice of magnetic impurities, another natural question that emerges is that of magnetic order. So if you're talking about few % of impurities, then there is no question about these impurities forming some kind of magnetic order. But when this is a lattice of impurities, then it is actually a full lattice of these magnetic moments. And now a relevant question is, how do we understand the magnetic order in these systems? And in this context, the RKKY interactions actually is one key sort of idea that emerges, where you can talk about the interaction between these two spin movements mediated by the conduction electrons. Okay? And if the number of magnetic impurities are large enough, then these RKKY interactions would lead to some specific magnetic orders, and you can have a variety of magnetic orders depending on the band filling and of the conduction electrons and so on. And you have another idea of double exchange physics, which is more relevant for, let's say, negative JK, where this is actually a ferromagnetic coupling, and this explains for example, or is a key ingredient in explaining the CMR effect in manganites. Something has come up here. Right. So to sort of summarize this, if you now think about the magnetic order in these systems, you can think of two limits of this model. In one limit, you have RKKY interactions. So this is the weak coupling limit, where you can think of this term as a perturbative term, and you can expand, second order perturbation theory in JK gives you a magnetic interaction between these movements mediated by the conduction electrons, and these RKKY interactions now can stabilize certain magnetic order in the system. On the other hand, you have the Kondo physics, where the local movements will be completely screened by the electrons, conduction electrons, and you will have no sign of a magnetic impurity remaining there. So the system becomes completely non-magnetic. And this was essentially summarized very nicely in this so-called Doniak phase diagram, where there is a competition between the RKKY scale and the Kondo scale, and depending on which is the dominant scale, you either have magnetically ordered phases or you have Kondo screened phases where there is no magnetic order. So if one thinks of let's say homogeneous phases only, then this is the full summary of this model, in the sense that this is all that can happen in this model. Either you have magnetic order, or you have a Kondo screened non-magnetic phase. But we know that the allowed phases can also be inhomogeneous, and this is indeed what is reported in these experiments. So this is what is known as partial magnetic order or partial Kondo screening. These two sort of names are used interchangeably, where what happens is that if you look at all the lattice sites where the magnetic impurity was present, so there are examples in multiple heavy fermion materials. So you find that in the ground state or at low temperatures, magnetic movement develops only on certain sublattice of those sites. So here you can see the spin arrows are arranged on some of the uranium sites, but this uranium site is empty, which means this particular site got Kondo screened, but not the others. And this happens spontaneously. So you have sort of a partial ordering of these impurities. And there are examples, other examples, cerium-based compounds. So you have this plus and minus, which refers to up and down spin, and then there is a zero, which means that there is no magnetic, there is no trace of magnetic impurity left there. So it's completely screened by conduction electrons. And in fact, although I'll be talking about Kondo systems, but this situation that a magnetic system can have a partial order can also arise in insulators. And this is an example from the insulating class, which is of course not relevant for the talk. But you can have situations where even in insulating magnets, you can have essentially sites where you have no magnetic moment developed, and there are other sites where you have magnetic order. Right. So now, what is the state of theory on this? And this is, I try to summarize it in the next 2 slides. So this is essentially slightly non-trivial mean field theories where you go beyond single site, and as you see that if you go beyond single site, then there is a possibility of having inhomogeneities in the order. So this is cluster dynamical mean field theory with 2×2 cluster, and this is on a Kondo lattice model, and I think this is a filling fraction versus Kondo coupling. And so what one finds is that, so this at low Kondo coupling, you have all the magnetic orders as would be dictated by RKKY interactions. Different kind of magnetic orders would appear here. And as you go to very high Kondo coupling, you expect a quantum paramagnet or a Kondo screened phase. But in between these two, one finds these partially ordered phases. In particular, here there is only one partially Kondo screened phase where a checkerboard pattern of sites have a complete Kondo screening and the remaining sites have a magnetic order. Similar results are obtained in this generalized Hartree-Fock scheme where you again look at conduction electrons as x-axis and Kondo coupling as y-axis, and between the magnetically ordered state, which is dictated by the RKKY interactions, and the fully Kondo screened state, there are these intermediate phases which are kind of a mix of magnetic order and Kondo screening. So this is from various kind of mean field theories, and now you also have quantum Monte Carlo simulations, and so essentially similar results are obtained with different details in quantum Monte Carlo simulations as well. These are results on 2 different models, a Kondo lattice model and Kondo necklace model, and these are results on periodic Anderson model, and this is variational Monte Carlo, and this is continuous time quantum Monte Carlo. And so the general story is the same, that between the magnetically ordered phase, which is the story of RKKY interactions, and a fully screened Kondo phase, you have intermediate phases where you have partial Kondo screening. And this partial Kondo screening, as you can see in this case, for example, can generate a sort of a new effective lattice structure, for example. So having seen all of this, now the question that we are asking is it possible to understand this partial Kondo? Yeah. Yeah. Oh, well, so I would say one would go for this continuous time quantum Monte Carlo. It is sort of least biased in some sense. So variational calculations are also biased in the sense that you have to construct your variational starting points, and you may miss out on some possible candidates there. Again, mean field theories are also, of course, biased by their very starting point. So I would say that CTQMC would probably be the best. Yeah. Right. So I mean, as you can see that this is, of course, these results can be obtained on the full quantum model, but these calculations are very challenging. So what we are trying to ask is there a sort of a simpler, intuitive way to understand these phases, or the possibility of these phases? And this is the main sort of topic of this talk. So the main challenge is that you have to actually somehow retain spatial as well as quantum correlations at some level, and this is what we attempt. So here is the general idea. So so you begin by realizing that so typically when you write down a Hamiltonian, immediately what we think of is that, okay, let's find the eigenstates of this Hamiltonian. But eigenstates, not always described, or the reality is not always best described by eigenstates. So one classic example of this is a Neil antiferromagnet, so which is not an eigenstate of the antiferromagnetic Heisenberg model. Nevertheless, thanks to the spontaneous symmetry breaking idea, this describes the reality better than the eigenstates themselves. So generally speaking, if you have spontaneous symmetry breaking in the system, which can be thought of as a sort of a bridge between classical and quantum description, then you can essentially replace the quantum operator by a classical variable, and it would still not miss out the key physics. So in order to address, or in order to include this partial Kondo screening or partial magnetic order phase, such phases, the question we are asking is that, is it possible to have this spontaneous symmetry breaking in such a way that it happens on a fraction of sites? So you have some given lattice on which the spontaneous symmetry breaking leads to local movements on certain sites, and it sort of gives the remaining sites as Kondo singlets or the non-symmetry broken states. And so if you look at this, the answer from what we summarized over last 2 slides seems to be yes, that it is possible both in experiments and theory to have such situations, right? And so now, can we actually make use of this idea to construct some models? And this is what we will attempt. So before going to that, so we ask a different question, which is, typically when you put Kondo impurities in materials, when you dope metals with impurity atoms, these impurities are localized in certain places. This is dictated by just the setup itself. Okay? Now we can ask the following question: what if these were not localized, and you asked what locations would 2 of these impurities would want to select if it was left to them? Okay, so you have 2 impurities and they can float around in the system. What locations would they want to finally freeze into? This becomes relevant because we want to talk about spontaneous formation of Kondo singlets in systems. So which sites are selected for formation of singlets becomes a relevant question. So if you look at this particular question in the small JK limit, then you would expect that these impurities should sit as close together as possible, because RKKY interaction decays with distance. So you want to gain from the RKKY interaction, so the impurities they will retain their magnetic character. So they should sit close together and gain maximally from the RKKY interactions. On the other hand, in the Kondo singlet limit, the Kondo clouds would be present around the impurities, and then these clouds would actually repel each other, and therefore in this large Kondo coupling limit, the impurities should repel each other. So the nature of attraction should be kind of attractive for small Kondo coupling and repulsive for large Kondo coupling. This, at least in a very simple model, we can test out this idea. So we take the model with, on a one-dimensional lattice, just 2 impurity sites, and you can exactly diagonalize it for very simple case of 2 electrons. So 2 electrons and 2 impurities. You can exactly diagonalize this problem and ask for what distances. So you can take multiple distances, and for a given distance, what does this interaction energy, which is basically the energy of this 2 impurity problem, minus 2 times the energies of the single impurity problems. That is essentially the interaction energy. So you can extract this interaction energy and ask, how does this interaction energy vary as a function of Kondo coupling for different distances, or for a given Kondo coupling as a function of distance, and so on. So this is the answer we find, which is actually in line with what I described in the last slide, that if you look at it as a function of distance, it goes down for large JK, and for small distances, the effect is very small, relatively small, but it actually increases for small JK. So the nearest neighbor interaction is given by this graph, and the next nearest neighbor is by this, and so on, as a function of JK. So this feature will be useful when we construct the model that I'm trying to arrive at. Okay, so now given this, we are ready to actually propose the model. So the model is the following. You take the lattice, and then you label at this stage completely randomly certain fraction of these sites as correlated sites, and the other fraction remains uncorrelated. So the story of the correlated sites is that we are assuming that on these sites, a Kondo singlet has formed. And the energy of this Kondo singlet can be written like this. And that energy now enters the Hamiltonian as simply a classical variable. Okay, so essentially one is using the Kondo singlets as an effective classical variable with its own energetics, and that goes to the Hamiltonian. Now what is this rest of the Hamiltonian describing? The rest of the Hamiltonian describes electrons coupled with classical local moments, which are these uncorrelated sites, right? So you have electronic kinetic energy, the local coupling with the blue spins now, and now the approximation is that the blue spins can be treated classically. There is no quantum spin here. So you have the electronic spin is quantum, but the local movement is classical. And you have basically the energy count from all the Kondo singlets and the interaction energy that we just talked about, the relative the inter-site interaction between Kondo singlets. These terms are there, plus what is this delta? The delta describes the fact that if there is a Kondo singlet that has formed here, then the rest of the electrons traveling to this site, that process is inhibited. Now this is something that is completely different in the Kondo lattice model. That process is at the heart of giving you resonances and so on. But here one is trying to look at extremely simple limit where you're saying that you're kind of separating out these two subsystems. So one of the subsystem describes Kondo physics locally, and the other is simply trying to describe conduction electrons interacting with interacting with the local movements, which are now treated classically. So this can be thought of as a Falico-Kimball version of the Kondo lattice model, where you have actually suppressed some quantum degrees of freedom further, but you have taken care of certain energetics, almost like a classical term. Yes. Delta is JK. Delta is exactly JK here. Yeah. Right. Okay. So now with this structure in the Hamiltonian, what you notice that this is now bilinear in electronic operators. There is no 4-operator term left here by this construction, and therefore we have a nice method to treat these problems, which is known as hybrid Monte Carlo. And the way the hybrid Monte Carlo works is that you basically have now optimization. You're left with an optimization problem where you have to worry about different arrangements of these singlets. So essentially, as I say in this last point, there are 3 things to be optimized over here. Total number of singlets. These are allowed to vary from 0 to number of electrons. All possible arrangements of these singlets, where they live on the lattice is completely determined by this Monte Carlo, and orientation of the classical spins on the non-singlet or the uncorrelated sites. So these variables are what are to be optimized by this hybrid Monte Carlo. And the way it proceeds is that you actually take an arbitrary configuration of these variables, and then you propose creation of a Kondo singlet from a normal spin or vice versa, and accordingly the energetics is taken care of. And at each step in this Monte Carlo update, you will have to still diagonalize this 1 electron problem. Okay, that's actually the heaviest step here. And you can proceed with this, and it turns out this process can be carried out reasonably easily with about 100 sites for about 100 sites, and you can analyze the data and look at the results. So this is what we find. So in fact, we can look at this right hand side picture first. This is essentially the fraction of Kondo singlets as a function of Kondo coupling. And for 2 particular situations, the number of electrons is as equal to number of sites, which is n e equal to 1, or number of electrons half as number of sites, which is sort of quarter filling case. So half filling case and the quarter filling case. So in the half filling case, you can see the first thing we notice is that you have a plateau structure in this Kondo singlets. So the plateau structure immediately tells you that there is a partial Kondo order that is present here, because only certain number of sites have become Kondo singlets. If we saw a simple 0 to NE jump here, that would have meant that the system does not prefer to have any partial creation of Kondo singlets. It wants to go from all magnetic to all Kondo. That does not happen here, and you have this intermediate, actually quite a broad intermediate region with the partial order. So this is represented as a phase diagram where we have looked at the details of the phases that are present, and so you find indeed at low JK you have the RKKY physics. This is given by this region where there is no Kondo singlet. You essentially have just the local spins treated classically, and they are describing the RKKY ordered phases for you. And as you go to very, very high values of JK, you will get everything into a very trivial phase in this model, which is just all spins are screened into or are labeled as Kondo singlets. But in the intermediate regions, you have phases where the Kondo singlets organize themselves in certain patterns, and the remaining sites have magnetic order on them. So some examples of the kind of phases that we get is this. So you have, this is I think 25% of the sites become Kondo singlets, and they actually emerge into this kind of a lattice where it becomes, if you look at just the lattice for the conduction electrons, it is a Lieb lattice. So on the square lattice, you have Kondo singlets formed on these alternate sites and alternate sort of layers, and the structure of this is exactly that of Lieb lattice now, and that reflects in the electronic density of states when you look at only the the nature of density of states of conduction electrons, taking into account the fact that each Kondo singlet site was having a repulsive potential, right, equal to Jk, and that there is a ferromagnetic order in the background. This leads to a ferromagnetic splitting of the density of states, the up band and down band, plus this the impurity band sort of, which in this model is pushed to this artificially sort of large values is equal to Jk. So the magnetic structure factor shows that it is a magnet. It's sort of a ferromagnetic order, and so this is one example of one of those partially ordered phases. And the other example turns out to be this one, which has dimer-like structure of Kondo singlets, and the remaining sites remain magnetically ordered. And here the magnetic order is described by this two-peak structure. So by the way, so in these calculations, we have actually assumed the spin to be of Ising type. That is actually, I think, is a little bit restrictive. So if you allow the spins also to be of continuous in nature, then it's likely that we end up getting more interesting magnetic phases here. And this is particularly true if you look at frustrated lattices, geometrically frustrated lattices, not so much on square lattice maybe. So yeah, so this then led us to this question that this is still restrictive in the sense that when we do this hybrid Monte Carlo, at each Monte Carlo update step, we will have to diagonalize the full one particle quantum problem, and then you accept or reject the moves based on that, and that limits the system sizes that one can simulate, and perhaps that limits the nature of phases that are possible, because so this is something that we thought of improving, and this led us to an idea that so we have already essentially removed one of the major complications of the Kondo lattice model, and in that sense it is really a toy model that we are looking at. The Kondo singlet has been treated as essentially a classical entity with its energetics. Now we can ask for the remaining quantum aspects of the problem, can one actually get rid of the conduction electrons completely and write down effective spin-spin interactions in the spirit of RKKY? And then you have a model which is completely classical. And so here we have actually come up with this idea to calculate the effective magnetic couplings beyond the RKKY settings. So in RKKY settings, you assume that that you have only two magnetic impurities and then there is a conduction band. So it's very clearly a perturbative problem. But here, when you have a Kondo lattice, then there are spins present at each site, and now it's not clear whether simply a perturbation taking two spins into account works. So here we found an interesting, let's say, a numerical approach which seems to work, and let me try to describe it to you. So let's take a paramagnetic arrangement of all the spins, and then I identify two specific spins, I and J, and my aim is to calculate the effective magnetic interaction between these two spins. So I consider four configurations of these, where as you notice, I am changing only these two spins. So configuration one is this one, where you have both the spins pointing in the same direction. Let's say this configuration has energy E0. So essentially, you can put electrons, your conduction electrons, into this classical spin configurations, diagonalize the problem, calculate the energy at a given filling fraction, and that's your energy of that configuration. Then I flip the spin at site J, and then you calculate the energy of this particular configuration. And then you calculate the energy of a configuration with the spin flipped at site I, but at J it is restored. And then finally, both spins flipped. Now, if I think that that all of this can be described by a simple Heisenberg model with any pair, sort of with long range side-to-side interactions, then any change that happens due to this spin flipping is actually accounted for by change in all the links that are connected to site J. Because site J has flipped, so if I calculate the effective change in energy between configuration E0 and E1, then that change comes from the changes that are happening in the links which are connecting all the sites to site J. Similarly, if I look at this configuration, the change in energy between E2 and E0 has to be accounted for by change in the links that are connecting site I with all the other sites. Finally, when I look at this one, here the link I and J is invariant. The link I and J does not change. So the change in energy here is due to all the links connecting site I to all other sites and site J connecting to all the other sites. So if I now take the differences of these energies, then you can actually check it out that this particular combination DE1 plus DE2 minus DE3 simply extracts out the coupling constant between site I and J. So of course, all of this has been done by keeping the other blue spins frozen into one configuration. So then you can actually think of some various kind of averaging. So you can think of calculating this quantity and then averaging over all possible orientations of the remaining spins. And this way you can calculate interactions between any sort of two pairs of spins. So the assumption here is that we are assuming that there is only Heisenberg type interaction that is present. If you assume other kind of interactions, then this idea will not work. And so you can compare, using this sort of idea, you can calculate now variations of these coupling constants with, electron concentration and the Kondo lattice coupling values and so on. So these are typical graphs for 4 neighbors nearest to the 4th neighbor as a function of conduction electron concentration, and the interactions sort of vary, change in sign and so on as you go from 0 to 1 in the conduction electron concentration. And this is also sort of changes with the details change depending on the value of Jk as well. So one of the tests for this idea is that you can compare it with RKKY. And it turns out that what we are doing exactly matches RKKY for small Jk, but it then deviates from RKKY, which is expected because at large Jk you don't expect RKKY to hold. So the numbers that we are calculating, they become not only different in magnitude, but sometimes also different in sign with respect to RKKY couplings. And so these graphs sort of give us confidence that the way we are calculating these couplings are probably correct. Of course, the assumption that only Heisenberg model describes the couplings would break down in various places, and that one has to worry about. Right. So then what we also did, we went ahead and computed the comparison between energies of different magnetic states given by the semi-classical model that was sort of introduced earlier, and this fully classical model. And this energy match again suggests that probably the energetics aspect are being treated reasonably well in this approximation. And so now, if the semi-classical model that was introduced before can now be replaced by this particular fully classical model. But there are some details here that one has to remember. So now these two terms will remain exactly the same. They are simply describing, these were already classical entities. The Kondo singlets and the interactions between Kondo singlets were already classical variables. So what we are replacing now is this particular quantum part by again a fully classical part. And here one has to remember that this is describing the paramagnetic energy, which is essentially keeping into account the fact that if you have certain number of conduction electrons present in this conduction band, that energy has to be accounted for. So that is the paramagnetic energy. This depends now on the number of Kondo singlets as well as the Kondo coupling constant. Similarly, the coupling constants that we calculated for this Heisenberg interactions, they also depend on the number of Kondo singlets present, because that affects the conduction electron density and the coupling constant as well, naturally. So one can actually go ahead and do simulations on this fully classical model. So this calculation of the coupling constant is a one-time affair. So you put that effort one time, that you create all the lists of coupling constants for the given model here. And then you can simulate the model now entirely classically. And this model can be simulated on much larger lattices. So we have just begun on this, and some initial results are here. So we indeed find that the partial orders with fractions 1/4 and 1/2 are obtained within this purely classical model as well. So this essentially brings me to the summary of the talk. So what we have done here, or what I've introduced in this talk, is the idea of a Falico-Kimball-like model specifically for treating the partial magnetic order in Kondo systems. If you ask for, if one has to be realistic, so this model cannot be cannot give you many other things related to Kondo physics, right? But specifically, if you want to look for the possibility of Kondo partial magnetic order in Kondo systems, where one is interested mostly in the arrangements of these magnetic sites and so on, then this model works out reasonably well. Some of them, so this is connected to Kondo impurity and Kondo lattice models, because some models can actually be explicitly calculated from those models. So on a square lattice, I presented some results where it shows that there is a possibility of a variety of partially magnetically ordered phases. And there is a proposal for classical Hamiltonian, which we are still working on. I think there is still some scope of improvement there. So this is very much an ongoing work. And what we want to really look at two aspects here. One is already at the level of defining the model properly. So we want to improve the connection of this model with Kondo lattice model, which is probably bringing in some more of realism of Kondo physics. At this stage, it is simply treated at the 0th level. I would say that you simply say that there is a Kondo singlet with a certain energy, and there's nothing more that is happening there. And the other thing that is relevant from experimental viewpoint is that many of these partially ordered phases are actually found on geometrically frustrated lattices, and we want to investigate this particular model on the geometrically frustrated lattices next. So I think that's all I had to say. Thank you so much.
Thank you, Sanjeev. Questions?
So I guess two related questions. So this phase diagram on the left, can you compare that directly with the continuous time quantum Monte Carlo, which you said?
So this, so I think this phase diagram, if you, let me go back to that. So in the phase diagrams that I showed before, this one compares the best with probably the Hartree-Fock, this one, where essentially there is a magnetic order from RKKY interactions at small Kondo couplings, and then as you go towards the fully Kondo screened region, there are intermediate Kondo, partial Kondo ordered phases, partial magnetically ordered phases coming up all over this place, right? So in this phase diagram with the cluster dynamical mean field theory, there is only one specific partially Kondo screened phase that came up, and in these particular phase diagrams as well. So this is actually done only at half filling, so this cannot be compared. This one, if you compare with the results, this only has one particular partially Kondo screened phase, but I'm not sure what are the details here. Maybe I've not looked at carefully. Like, what is the nature of the magnetic order in the background here? So direct comparison is so. The feature that matches with all of these results is that between magnetically ordered phase and a Kondo screened phase, so it is actually other way around, antiferromagnetism is here. So between a magnetically ordered phase and a fully Kondo screened phase, there is a partially Kondo screened phase. That feature of the model matches with all the all the models that are discussed here in these two slides.
Okay.
But details, I'm not sure.
Okay, yeah, thank you. And then the second part of the question was, is your main motivation really the last point in your conclusions?
Yeah.
That you want to study those frustrated lattices where the quantum Monte Carlo would not work? It's going to have a sign problem, I assume.
Right, yeah.
Okay, so that's really the key point in what you're doing, to get access to those lattices.
Right.
Okay,
exactly.
All right, thank you.
Thanks.
So I just had a question about, so are there interesting physics associated with like somehow these kind of Kondo singlets undergoing some kind of percolation transition where it kind of decouples the magnetic moments, or is there anything interesting, especially at finite temperature? These are
okay.
moving around or fluctuating.
Right. Yeah. So as I said, that feature is kind of inaccessible to us right now, because the Kondo singlets here are essentially like classical objects. So this is what I meant when I mentioned that we want to improve the connection with Kondo lattice model. That can you actually add further features to this model? Maybe some what happens with the hybridization of some kind between these classical like Kondo objects and the conduction electrons. So at this stage, if there is any physics related to percolation of Kondo singlets and so on, that is very naive, I would say. It's just that it's classically it's sort of like a phase separation between two kind of phases, two extreme phases. Yeah, no better answer at this stage.
Any other question? Okay, if not, let's thank Sanjeev one more time.
Thank you.
Next, we have a contributor talk by Yogendra.
This is fine. Yeah, thanks. You can hear me, right? Thanks. I would like to thank the organizers for the opportunity. So I'm going to talk about fractional Vanier orbitals and tight binding gauge fields in Kitai model with flat band Majorana bands. So here is an overview of my talk. So I'll be talking about first construction of low energy tight binding models for the fractional particles in the background of gauge fields, and then I'll discuss flat bands and Vanier orbitals and fractional Chandni insulator phases for Majorana fermions. This is based on this reference done with Professor Bhaskaran and Tanmay Das. To give a context of the problem, let's consider the antiferromagnetic Heisenberg model. For two sides, the ground state will be simply the nil state, up-down state. Let's say, but when you have frustration in the model, so we can have all kind of spin configurations allowed in the state. But at low energy, only singlets will contribute. The triplets will have high energy states. So to get the low energy physics, we have to impose a constraint on the allowed Hilbert space. So that will generally give rise to gauge fields. So the gauge fields will emerge in the low energy physics. And the single spin flip excitations will give rise to high energy modes. But when you apply some external fields or something like that, and then couple these gauge fields and the matter fields, so the interesting physics arise. So one such example was done in this work, where we found some kind of a glassiness in the Kitai model without having to do with any disorder present in the model. So here that is mainly due to restricted dynamics of the excitations. Here the excitations have fractional statistics. So that is the main reason for the glassiness present in this model. So mainly the gauge sectors, different gauge sectors will give a platform to manipulate these fractional particles. So that is what my main goal is to do here. So in this talk I'll discuss the low energy effective tight binding model to these fractional particles, mainly keeping them in mind that like there is a flux in the background, so I have to keep that in mind, and then I have to satisfy the constraint which is present in the background in constructing the low energy theory. So this I'm going to do it in Kitai model. Kitai model is originally written in spins. So, but if you take Majorana representation for the spins, this will simply look like this, where the C operators are the Majorana operators, and U operators are gauge operators, which are Z2 operators, which takes +1 and -1, which leaves on the bonds between site I and J. So if you take all the products in the given plug weight, 6 U operators in the plug weight, it will measure the flux passing through the plug weight. So if you take this multiplication to be +1, it gives rise to 0 flux, and if it is -1, it gives rise to pi flux. So just by arranging these fluxes in a given manner, we can tune the Majorana dispersions and all. So here I am taking one such example denoted by 2x2 configuration, where 2 is the distance between these pi fluxes. Just by taking this kind of a configuration and fixing these U operators, this will simply look like a Majorana hopping in the background of some super lattice. So this will right away give the band structures and all. So here is the band structure. This is for the next nearest neighbor hopping k equal to 0. This is for k not equal to 0 case. So as you can see, these bands are very nearly flat. By tuning k, you can tune the bandwidth and the gap between these bands, low energy bands. So by changing the distance between the flux also, one can tune this bandwidth. So you can make them even more flatter and flatter. So here my goal is to construct a low energy theory for these bands which are close to the zero energy. So the way to do is that this is a general procedure. I may not need this much thing for the Majorana construction and all. So the general procedure is to take the original Hamiltonian and construct a self-consistent super exchange kind of a potential H prime, and then project out to give rise to the effective Hamiltonian. Let's say if I'm considering P bands in the conduction band and P bands in the valence band. This model we have a particle hole symmetry, so they have equivalent number. So if I just to take this whole Hamiltonian, the way to do self-consistency is to write the general hopping kind of Hamiltonian in the momentum space, and then fit this hopping terms with the general band structure. So here the hopping parameters, I mean the real part and imaginary part make direct connections to the metric and gauge freedom in the problem actually. So by fixing this imaginary part in such a way that it gives rise to the flux present in the model, one can fix these hopping parameters and then we can study further the effective Hamiltonian. So I will give you an example where let's say I am considering here 4x4 flux configuration for the Majorana. So the first step is to construct the binary orbitals for these Majorana fermions, and then I can fit the hopping Hamiltonians, keeping that in the given unit cell there is one pi flux residing in the unit cell. So I have to keep that in mind and then fit the band structure accordingly, and then I'll get the effective band Hamiltonian. So here there is a catch for this Majorana fermions to do linearization. Here we have to impose particle Hall symmetry in every process, like in constructing the trial wave functions and in taking the unitary matrices also. So the Majorana orbitals here are like a superposition of the electron hole orbitals in some sense. So I have to always consider the particle hole symmetric bands here. So this is how it is done. So and then let's say after I get the effective Hamiltonian, I can construct all the invariants of the bands. So here I am plotting the quantum metric and Berry curvature are the invariants here. If I can write some scalar invariants out of these metric and Berry curvature, from Berry curvature I can point out chain number, and from quantum metric I can write some invariant quantity G. Here I am plotting those quantity for comparing with the pi flux, 4x4 flux case and the 0 flux case, and there is a huge change in the in these quantities, and there is a interesting phase transition here that I am not going to talk about. So interestingly, these bands satisfy the conditions to be an ideal chain insulators. Those are these uniform Berry curvature and this trace condition where trace of a quantum metric is approximately equal to Berry curvature at each k point. So these are the kind of ideal conditions for the chain insulators. As you can see here, I am changing for different k values. I am plotting the Berry curvature and the difference between these two quantities. So as you can see, for the higher k values, we have a very uniformly distributed quantities. So at these scales, so if I take any interactions among the Majorana fermions, I can get fractional chain insulators. So these are discussed in these kind of these references. So now I'm going to discuss gauge invariant mean field theory to study the fractional chain insulator phase for this. I mean, there are many numerical calculations to understand the fractional chain insulators. I think we wanted to try analytically with a minimal model. So I took the effective model and then took some interaction Hamiltonian, where these are all 4 in number. These are all Majorana fermions in the effective model, and these are the gauge fluxes residing in the 3 nearest neighbors between these 4 Majorana fermions. Like these are the 3 nearest neighbors of the honeycomb lattice. So here I am considering some mean field parameters. So this is not sigma 1, this is sigma 2. So I am considering 2 mean field parameters, where these mean field parameters are also kind of not they are dictated by the gauge fields. I cannot take simply anything I want. So I have to follow these gauge rules, where I have to take care of the gauge freedom residing in these 2 bonds. So here I am forming, here is a mean field Hamiltonian, where this effective Hamiltonian is 2 by 2 Hamiltonian, and then I am taking some general mean field terms with some density kind of order in this case, where Q is I have taken to be G2 by 2. So here effectively there are 2 bands in the original model. So I'm by doing this, I'm getting 4 bands in this case. So the distribution of the orbitals in the 2 bands is getting redistributed into 4 bands. So if you calculate each band Chern number, they will comes out to be fractional in this case. So here this fraction can be anything, but by keeping stable mean field parameters, one can get the discrete kind of a fractional Chern numbers. So this we are going to do further and all. So if you have any doubts, you can check this reference. So to conclude, I have discussed how to constructing topologically non-trivial flat bands for the Majorana fermions and the Vanier orbitals and tight binding effective models for the fractional Majorana particles. Then I discussed the fractional chain insulator phase for the Majorana fermions using some mean field theory. So that's all. Thanks.
Questions?
If your system exhibits this fractional churn insulator of Majorana fermions, is it going to have a thermal transport signature? Or how do you observe it experimentally?
I mean, here, let's say, here by applying mean field theory, we are just folding the bands and then gapping them out. So we have to tune the density of Majorana. I mean, we can do it by forming a complex fermionic thing and then tune the Majorana density and then keeping at the low energy band. Then one can get the fractional chain number.
I'm asking about the signature. So let's suppose that you've got in a system, you're lucky to get a magnetic system which realizes this. And what experimental signature would there be of the fractional churn insulator?
I mean, one can have gapless modes carrying the fractional charge. I mean, that's the kind of.
Yeah, so I guess what is that? So how would you see the fractional charge? I mean, in the non-interacting case, you would have this quantized thermal transport. But when you add the interactions in, I guess I'm asking, so how would that change?
I mean,
how do you see the interaction
so what I'm saying is related to fractional quantum Hall kind of a physics, where one can see the edges, different kind of edges, which can give a fractional.
You have charge in that case. It's a little bit easier.
Yeah, here I don't know. Like maybe one can calculate with a thermal Hall kind of a.
Okay, thank you.
Yeah.
Any other question? Okay, if not, let's thank Yogendra. So that's the end of the session. We'll break for lunch. Today we have a change in the timings are not the same as last week. We'll meet at 2:15 after lunch, not 2:30. It will be at 2:15. Thank you. So for those of you who have come in this week, the lunch is arranged towards that side of the campus. You can just follow the people who know the way. Thank you.